Okay, in this video we're going to learn how to do a shader. So this is the shader code running right now, and as you can see you have several effects going on. So you have the specular reflection, you have the shadows, and you have the diffuse light, diffuse shadow. So basically the sun doesn't reach here, so there's no light being diffused from here. So let's see. As you can see, the moon also is going to get blocked by the shadow at one point. You see it's gone, and then it should appear on the other side. Yep. Okay. And the specular reflection is essentially the reflection of the sun from the surface of the water. So I'll explain that in a little bit. But as you can see, it's just like like if you were to look at the sea on Earth and you would see the sunset, you would see the same effect. Yeah, so okay, let me go to the code. Okay, so here we go. Okay, so the shader consists of three different effects. You have diffuse light, you have specular reflection, and then you have the moon shadow calculation. So we get the normal of the vertex. So this is the vertex shader. So the normal of the vertex, essentially, since we have a sphere, we know that that all the normals point outwards, right? So the normals would point away from the sphere. And if this is the sun here, then we calculate the dot product between the normal and the light direction. So let's say this is the light direction. So we calculate the normal, and all right, maybe it's the other way. It's probably this way. So this is the light direction. So when they're in line, that means that the dot product is 1, and when the normal is over here, then the dot product between this vector and this vector is going to be -1. So we see that here. So if so basically on this side, the normals point in a direction that's facing the sun, and here they're pointing away. So this is our diffuse light contribution. Okay, so now we're going to go to the specular reflection, and essentially we have the light position and we have the camera position that we have to take into account. So let's say this is the camera. So let's say this is the eye here, and I think my vector points this way, so therefore there's a negative sign here. But essentially, oh crap. Okay, one second, let me see. Yeah, okay, specular reflection. Okay, so essentially we want to take the average normal between this guy, this vector, the vector from the center of the sphere to the eye, and so this is called our camera normal. So this is our camera normal, and then this vector is called our light normal. And we're trying to find the average. So this is going to be the specular normal. And basically we do that by normalizing this vector and this vector, and then adding them together, and then normalizing them again. And that basically gives us a normal that's the average between, like this. So this is the specular normal. And again, we're calculating the dot product between the vertex normal and the specular normal. And when they're 1, essentially that's the maximum value. And after anything, any vector that's not exactly aligned is going to be slightly less than 1. So in this code here, we are multiplying the specular light. So essentially, we're taking the power. And as you know, if you have a graph that looks like this, let's say this is 0, this is 0, and this is 1. Put it here, 1. This is 0 here, and this is 1 here. Then when we take the power, then that essentially keeps 1 at 1, but it makes all these values that are less than 1 go to 0. So essentially, we're gonna go to this type of plot after. It's gonna look like this. So this is the 0, and this is the 1. Oh, sorry. Okay. This is the 0, and this is the 1. And this is the theta. So if we look at our example here, basically that's what we see. You see this spot here, that's the specular spot, and because we took the power, it's concentrated where the average normal equals the vertex normal. And that's the same way we generated this sun. So it's essentially just a dot product of this direction, of the light direction, and then we took the power over and over to concentrate the light in one spot. Yep. Okay, so let's go to the final light contribution, which is the moon shadow calculation. Okay, so essentially we we have the shadow position, which is basically the moon position, and the light position. And notice that we are multiplying by the transpose of the model matrix. This basically transforms these vectors into the vertex coordinate system. So we're going to start our iteration at pose, which is the vertex position, and we're going to set our velocity to be in the direction of the light, towards the light, right? And we're going to iterate. So I know exactly the distance between the two objects, so I know I have to iterate 100 times if the delta here is 0.01. And if we get close enough to the moon such that the distance from x to the moon position is less than the moon size, then we say that intersect is true, and we break out of this loop. And then here's a more fine calculation. So we know that we have intersected, so therefore we want to find the exact point of intersection. So essentially we just take the delta here and make it smaller. And I know that I have to do 1,000 iterations. You could do something more clever here. You could do maybe a zero finder algorithm, such as Newton's method or regular fallacy algorithm. But this is just a cheap kind of quick and dirty kind of intersection code. And when we do, in the second pass, when we do get close enough to the moon, such that the distance from x is less than the size of the moon, then we calculate the intensity of the shadow, which is going to be the dot product of the vector from x to the center of the moon and the light direction. So that means that that those vectors that hit the moon right on are going to contribute the biggest shadow, versus the vectors that hit the moon at a 90-degree angle. So let me actually draw that. Okay. Let me see. Let me go here and delete all this stuff here. Okay. Okay, so this is still our light position. And let's draw another circle here, and this is going to be our shadow position. Which is basically the vector. Let me try this. Okay, so it's the vector from the center of the Earth to the center of the moon, and the light position is this guy. It's the vector from the center of the Earth to the light position. Okay, so that means that we are. So let's say we start here. Let's say this is our x. Let's say x is over here. So this is x. And then we try to move in the direction of from x to the light position, which is honestly, the light is so far away that that it's basically all these lines are parallel. So the light is very, very far away. Okay, so in this case, we know that we intersect. So we do our iterations at 0.01 steps, and then we intersect, and then we do this finer calculation where we find the exact point where the intersection occurs. So that's here. And basically, the intensity is the dot product of this, let's call it x prime here. So this is the intersection position x prime. So so we have the vector from x prime to the center of the moon, and we have our light position, or light vector, which is this way. So when they are essentially almost parallel, then we know the intensity of the shadow is at a maximum. However, let's say we start here, and then we just barely graze the moon. So that means our x prime is going to be over here. And then when we calculate the vector from x prime, or the dot product from this vector from x prime to the center, and the light direction, light position, then this dot product is going to be closer to 0, in which case the intensity is much smaller. And once again, we're doing the power trick here in order to make the shadow more concentrated. Okay, so let me show you here. Okay, so the converse calculation happens for the moon as well, where the Earth serves the place of the moon for the moon, and of course the radius of the Earth is much bigger. So that means that every vertex on the moon gets blocked by the light gets blocked by the Earth, right? Okay, so let's wait a little bit. Okay, so here's the moon coming. Okay, so any minute now. Okay, here we go. So as you can see, the edge is blurry, and that's from the dot product and also the power trick. If we didn't do the power trick, and the dot product, the edge would be very sharp, but there are some artifacts with that, so that's why I try to make it blurry so the artifacts are hidden. Okay, well that's basically it in terms of our light contributions. So we have the diffuse, specular, and shadow calculations. And then in the fragment shader, essentially we pass these three components, diffuse, L spot, and S spot, to the fragment shader, and basically we add these components to the color. So the color is the texture that we got for the Earth and the Moon, and we add on top of that our specular and shadow contributions. Okay, well, that's it.